In this video on basic organic chemistry, we're going to talk about reaction mechanisms. Now, this video is just the basic video to allow you to understand how to do the reaction mechanisms, which are further on in the course. So it's really, really important that you understand heterolytic fission, homolytic fission, and radicals. And that's the main three things we're going to go over. So, first of all, bond fission. Now, if you've done physics, you will notice that fusion is to join atoms together and then fission is to break atoms apart. So we're going to break those bonds. Another word for breaking is cleavage. So cleavage of bonds done through movement of one electron or the movement of two electrons. Now you notice it says half-headed arrow and double-headed arrow. So what does that actually mean? So if we do this, we can say a half-headed arrow is going to be like this, and it's only got that half of the head. If we go for a double-headed arrow, like that, but it's got a full head like that. And what that means is it means there is the movement of a certain number of electrons. So in this case, we're talking about one electron, and then we do here, we're looking at two electrons. So I can say, look, one electron, let's do it as a dot here, is going from here to here. Now, that one is not strictly on the course, okay, but I will discuss it briefly just to get you to understand what's going on. So it just means movement of one electron from one place to another. And then we look at this one, this will mean the movement of two electrons from one place to another. And what we're going to do is we're going to give you a context of that. We're going to take you into some different molecules and show you what these actual arrows mean when it comes to reactions. So now we know about the two different types of arrows. We're going to do heterolytic fission. Now, look at that word straight away. Think, what does that mean? So hetero meaning different, and lysis meaning to break. So we're breaking up, and fission also means breaking of bonds. So therefore, we're breaking up to create two different species. And we do that through both bonding electrons going to one atom. And those two different species are a positive ion and a negative ion. And hence we call it hetero or heterolytic fission. And it's really important in your exams you can label heterolytic fission. Now it's quite simple because it uses a double-headed arrow. Now we've got a tip for here, and the tip is if you've got these double-headed arrows, which is what you're going to use throughout the entire course, they must come from a bond, a lone pair or a negative charge. Now a bond has two electrons in it because all covalent bonds are a shared pair of electrons, so two electrons. A lone pair is two electrons. A negative charge is as a result of an electron being gained, so it's a pair of electrons still that can move. So all of these are a pair of electrons, so you're going to use this double-headed arrow each time to move that pair of electrons to create these different species. Now the first species we're going to talk about is the simplest one we can, which is H and HF. Now, F is an electronegative element. Because it's an electronegative element, the electrons are just a little bit closer towards the F. Now, this happens all the time. Heterolytic fission tends to happen if you've got an electronegative element, and normally because something comes in to force something else out, which is the electronegative element. So there is your arrow, and it's telling you that those electrons right here will go onto the F. So they'll go onto the F. That means one of these electrons was the hydrogen's electron. Because it was the hydrogen's electron, that hydrogen no longer has any electrons. So therefore, I draw the hydrogen like this, and it's lost and becomes a proton. Now if we draw the fluorine as a result, it's easier to draw all the electrons on fluorine just to make this completely make sense. There's your electrons on the fluorine, okay, as it would be, and that electron here, this one on here, the dot, is this one here. Now I've moved both those electrons on, so I have to draw that cross because that cross is on there as well. That means fluorine normally has 7 electrons, it's got 8 electrons, got an extra electrons, so it becomes fluorine minus. So I wouldn't normally draw that like this, okay, I'd normally just draw it simply like this. So if I want to rub that off there, I normally just simply draw it as F minus. Okay, and that's because both of those electrons have gone onto there. And like I said, can come from a negative charge, because also that negative charge is due to a pair of electrons which I've just drawn. So if we then go to another one here, and we'll go to a bromomethane, like that. Okay, so we've got this, and we've got, okay, the Br is electronegative again. There's our lone pair of electrons, bonding pair of electrons, and that's going to go onto the bromine. That goes onto the bromine. Let's not forget our dipoles, because when we're doing mechanisms later on, the dipoles are really important. They get you an extra mark. From there, the bromine is gaining the electron from the carbon. The carbon has lost an electron, and so we end up creating this positive ion, and we create the Br minus, because both electrons have gone on. So we've got heterolytic fission happening in two examples, both where the double-headed full arrow has taken the bonding pair of electrons, put it onto the electronegative atom. Okay, and really, really important, and I'll just finish this off here, that you remember your dipoles when you're drawing them out. So if you haven't drawn your dipoles, make sure your dipoles are drawn. The arrow is going to the electronegative atom. Both electrons are going on there, which means that this has lost an electron, positive cation, and this has gained the electron, negative ion. And this is an example of heterolytic fission. We're now going to move on to talk about radicals, and radicals happen because of something called homolytic fission, which we'll do after this. But first we want to explain what radicals are. Now, they're a species containing unpaired electrons, and they're dangerous, really, really dangerous. So if you look at people who spend a lot of time in the sun, you can see their skin sags, and they can look a lot older if they go into sun without sunscreen on, without looking after themselves and things like that. That's because the sunlight shines on your skin, and what it does is it breaks the bonds inside your skin. For example, the collagen and things like that, breaks it into different parts. And when it breaks it into these different parts, the parts they create are called radicals. And those radicals are very, very reactive. And so what they do is the collagen itself starts breaking down. And as you get older, the collagen doesn't build back up. It doesn't have its relative strength. And so your skin starts to sag, just like you can see. I'm getting a bit older here. Okay, so these radicals are really, really reactive. Really, really reactive. And we'll talk about that later when it comes to reactions of alkanes. But what are radicals? How do you get them? So, with that reactivity and their dangerousness, let's put that to the side. And let's talk about how you actually do them. So, the simplest radical you're ever going to come across is going to be chlorine. So, try and draw chlorine now. So, try and draw it. Don't wait for me. Pause this, draw chlorine. And what you'll notice when you draw chlorine is that chlorine has 7 electrons in its outer shell. So there's my 7 electrons in my outer shell. And this is normally chlorine, and you don't find chlorine in this state very much. And you notice there is one single unpaired electron. So that's your unpaired electron. Now if you've got an unpaired electron, very simply, it's called a radical. And that's incredibly reactive. It wants to react. Okay, which is why you don't find chlorine as a radical most of the time. You find chlorine as Cl2. So this is not a good thing. Okay, very dangerous, very reactive. Now, if you're in the exam, you have to draw this like this. So you have to call it Cl dot. So you don't have to draw any of these. You just have to draw this single unpaired electron. So if you're in equations or something like that, and we'll talk about that in terms of ozonolysis in certain places, and we'll talk about that in terms of other reactions of ozone as well. And you'll have to write this in the equations as dot. So any radicals that just have one single unpaired electron, you have to write as dot. But there can be other things, and sometimes these are called biradicals. So let's draw this. This is oxygen. And oxygen, again, doesn't appear as O, it appears as O2. Now this one has 2 single unpaired electrons. Okay, it's still a radical, of some sort, but there's a really important exam point here. And the exam point is that you don't have to draw the dots. So if you put it into an equation or anything like that, if it's a biradical like this or diradical, you don't have to draw the dots. You can just draw it as O. And that's an important exam point moving forward into the future. Now that we know what a radical is, we're now going to identify the link between a radical and an ion. So a radical itself has the right number of electrons. So we're going to start from the radical and just draw the number of electrons in carbon and hydrogen and go through it. So, well, count the number of electrons. So if you look here, we're going to go for radical, and the radical for there will be CH3 and it will be CH3 dot, because it's a radical. Now if you think about that, carbon has a certain number of electrons. So the carbon will have 6 electrons. It's in group 4. And then each hydrogen will have 1 electron. So therefore this will have 9 electrons, because you've taken the 6 from the carbon and 1 from each of the hydrogens. Then we look at the protons, because we want to see that it's neutral. So again, 6 protons and 3 protons from there, which is 9. So I'm going to call that P+. Okay, so therefore it's neutral. It makes sense. It is neutral. Still very reactive, but neutral. If we look at that and we go to the anion, to turn that into an anion, a negative, we have to add an electron. Okay, so we want to make, this time, we want to make CH3, and we want to make CH3 minus. So we're making CH3 minus, so let's look at that. If that's CH3 minus, that will have, again, we'll look at the electrons first, 6 for that, 3 for that. That's what you'd normally have, but I've now got a negative. Well, the negative is because I've had an electron added. So I would have to add 1 to that to make it into this. So therefore, that is 10 electrons. Now, the number of protons is not changed because this is an ion. So the number of protons is not changed. So we have that. We then go across and we say the cation. Now, to make a cation, you have to lose an electron. So therefore, if we say CH3 plus, okay, we then have to lose an electron. So if there's 9 there, we have to have 8 here. And then as a result, we don't change our protons again. It's exactly the same. So as you go across 8, 9, 10, all we're doing is varying the number of electrons to get what we want. Okay, let's do exactly the same thing, and let's do it with OH. Now, when you go to OH, again, I'm just going to draw the radical. So that's going to be OH dot. So if we look at OH dot, let's look at the number of electrons in the oxygen. The number of electrons in the oxygen is going to be 8, because it is in group number 6, and it's got 2 electrons in the outer shell, so it's 8. And there's 1 of those, so that means 9. So actually, it has exactly the same as this. Then the protons, exactly the same, 9 protons. Now, neutral, so that's how I can quickly do that. We then move across, and we're going to go, right, okay, this time we want to draw OH minus. So OH minus, I have to add an electron to do that, so that means I'm going to do exactly the same. So, and you're noticing, hopefully very quickly, that the numbers here and here are the same. Okay, and that's a really good trick. So if that's the case, and this time I want to make OH, but I want to make OH plus. Okay, and again, it's exactly the same as the one above. I lose an electron. Okay, and then there we go. Now what I haven't discussed, because you never know, it might be asked, is how many neutrons are in all of this. Now, to make it from a plus to a radical to a negative, you don't have to change the number of neutrons, so we could calculate 1 and it will be the same for the rest. So there's 6 neutrons in carbon, and there's no neutrons in hydrogen. Normal hydrogen has no neutrons. So overall, this would have 6 And then because we're not changing it, this would have 6, and this would have 6. If we then look at this, the OH, how many neutrons are in O? Hopefully you've got to the fact that it's 8, okay? So that would be 8 neutrons, and again, we're not changing the neutrons, so as you go across, 8 neutrons. So what I've tried to show you here is the difference between an ion, a radical, and a cation, a radical, and an anion, just by movement of one electron, either decrease, losing an electron, or gaining an electron. This can easily be put in a multiple choice question in an exam to get you to identify what is the right number of neutrons, protons, and electrons in one of these species. In our final example in this video, we're going to talk about homolytic fission. Homolytic fission is where you break, again, the word lysis, and then homo meaning the same, and fission meaning breaking bonds. So we're going to break bonds to create two of the same type of species. Now, how do we do that? We do that by moving one electron, goes to each atom within the bond. And if one electron goes, you will create an unpaired electron, which is called a radical, as we've just done. And radicals are the same type of species as each other, and hence the word homo, because it means the same, it's the same type of species. Now, this is often initiated by heat or UV. So really, really important that you see UV and you think, right, okay, radicals, and that's especially important when you do reactions of alkanes later on in another video. So there's two types of examples we want to show you, and we'll do that now. So we're looking at FF here, and we want to take that FF and we want to make it into two separate species. Now, what I'm going to show you is not actually on the course, but it helps you understand how to do it. So let's take our F, and let's take, there's the electrons in the center of that bond, there's your covalent bond. Let's take one of them, this is our half-headed arrow, there, and one of them there. So we're basically putting them out, one electron there, one electron there. That means we'll create an F dot. But we're creating two of them, one of those and one of those. And we simplify that by just putting 2F dot. Now, if it's 2F dot, I know you may be thinking, shouldn't it be 1F dot and 1F cross? But we're just simplifying it because we only use the dot and the cross to show different elements in bonding, and there's no bonding going on here, so we just simplify it and say, look, 2 dots. Now, if that is the case, and we look at the CH4, and we draw the CH4 like it normally would be drawn, and there you go, and you say, I'm going to shine UV light at that, because it's initiated by heat or UV, shine strong UV light at that, and what's going to happen is one of these bonds is going to break. Now, that, as I said, the arrows is not on the course. You do not need to worry about ever drawing these arrows. But just think about it. What's going to happen if one of these bonds breaks? Well, one of these bonds breaks, and we're going to choose that one right there. So this one right here. Okay, and if that breaks, it's no longer there. One of the electrons is going to go here, and another one of the electrons is going to go here. So what you have there is have an example of showing it through these mechanistic arrows, and you can see that you create these radicals. And you have an example here where you're just making the radicals without the arrows, because, like I said, you won't need the arrows. This is just for understanding the process. And often you'll see above this UV. And I say heat or UV, but UV is the one we predominantly use in homolytic fission.